Good morning students. Today in our session we are going to continue the remaining part of atomic structure. So let us see which topics we are going to cover in today's video, that is Heisenberg's uncertainty principle and quantum numbers. Okay, let's start our class with Heisenberg's uncertainty principle. Okay, see what is Heisenberg's uncertainty principle. Heisenberg is a scientist in 1927. He presented a principle known as Heisenberg's uncertainty principle. What is meant by this uncertainty principle and what is the statement delivered by Heisenberg? See here. See, in Bohr's atomic model, while we are studying, electrons revolve around the nucleus in a particular path. So they will exchange their energies, but they don't lose their energies and they will not fall into the nucleus. This is the statements we have gone through in the Bohr's atomic model. But according to the Heisenberg's uncertainty principle, it is not possible to determine the exact position and momentum of an electron while it is revolving around the nucleus. Okay, means when any particle, any object which is in the size of an electron, not the bigger particle we are talking. If you take a big stone, if you are throwing that, so we are able to see that stone where it is. Suppose see here, this is this much bigger particle. Just if you throw, so we can track where the stone and where it is falling. Everything we can track, but the element or atom which is very small, like electron, subatomic particles, that much small particles or anything, if they are throwing where they are, we cannot identify the exact position and exact momentum. Means either we can find where is its position or we can find where is that momentum. Understand? So we cannot find exact position and momentum both simultaneously. Okay, at a time same where is the electron, like we cannot track that when it is in a revolving round the nucleus. So that is what Heisenberg's uncertainty principle, that is, it is impossible to measure simultaneously. That is the question. Simultaneously we cannot measure the exact position and exact momentum of an body small as electron. Any body we cannot track exact position and its momentum. That is the Heisenberg's uncertainty principle. And also we have one limitation for Heisenberg's uncertainty principle. Only this law is applicable for the size of the particle which is like electron, not for the bigger particles. This Heisenberg's uncertainty principle is not applicable. Okay, very minute 0.01 milligram size, 0.1 milligrams, this size of particles only able to follow this rule. Okay, this is Heisenberg's uncertainty principle. The Heisenberg has given one expression for this one. See here, delta x into delta p is greater than or equal to h by 4 pi. Delta x into delta p which is greater than or equal to h by 4 pi. This is the equation he has given for Heisenberg's uncertainty principle. But what is meant by delta x? Delta represents always a change. X here indicating the position, means change in position, and p means delta p means change in momentum. Okay, change in momentum always greater than or equal to h by 4 pi. Here see this momentum, already we know momentum is nothing but mass into velocity. So there is no change in mass but there is change in velocity. So while writing delta p we can convert this formula as delta, here I will write delta x into m into delta v is greater than or equal to h by 4 pi. Then delta x into delta v greater than or equal to h by 4 pi m. Here h is constant, Planck's constant, pi is a constant, and m is mass of electron is constant, 9.1 in 10 to the power of minus 31 kg. So this is a constant. Delta x indicates the change in position and delta v indicates the change in velocity. Okay, this is Heisenberg's uncertainty principle, as it has a one limitation, that is only this Heisenberg's uncertainty principle is applicable to the size of the particle or atom or any body which you are taking, that is should be as the equal size of the electron. That is only this is applicable. Okay. Then comes to the next one, quantum numbers, which is very important in atomic structure. And also we can get some compulsory question from quantum numbers also we can expect from JEE, right. See, what are these quantum numbers and why we are studying these quantum numbers in particular chapter. See, if we want to address one person, we have to know some information about that particular person, means in which city he is staying, in that city in which area he is staying, in that area in which apartment or in which number, that house number we should know, and again that particular apartment if you consider, again in which flat he is staying. All this is the information we should know to meet one person, means to address one person. Like that only here in atomic structure, we want to address one electron, we should know where is that electron, means in which shell it is, first shell or second shell or third shell, again in that shell or orbit, in which orbital that electron is present, s orbital or p orbital or d orbital or f orbital, in which orbital that electron is present. Again each orbital can accommodate 2 electrons, so either we are talking about first electron or second electron in that particular orbital is also we should know, right. So then only we can identify where the electron exactly present. Suppose if I say hydrogen has only 1 electron, suppose I will take nitrogen, what is the electronic configuration? Suppose nitrogen has 7 electrons, right. Nitrogen's atomic number is 7. I am talking about the 5th electron of nitrogen. Where will be the 5th electron of nitrogen? I want to address that 5th electron of nitrogen. So first of all we should know where is that 5th electron, means in which orbit that 5th electron is present, again in that orbit in which orbital it is present, again in that orbital either it is in a first electron or second electron we should know, right. So this is the information we can get from the quantum numbers. These quantum numbers helps us to address the electron in a particular orbital or in a particular orbit, right. Okay. See here, this is the study of purpose of the study of the quantum numbers actually. So here we have a 4 quantum numbers proposed by different scientists. Okay. Come to the first one, principal quantum number. We have a 4 quantum numbers. First one principal quantum number, second one azimuthal quantum number, third one magnetic quantum number, and fourth one is spin quantum number. These 4 quantum numbers helps us to address the electron where it is exactly present in an atom. Okay, that is the purpose of study of quantum numbers. Okay, let us start with the principal quantum number. See, principal quantum number was proposed by Bohr, Niels Bohr. Already while studying the Bohr's atomic model, I have explained that he proposed one quantum number that is called principal quantum number. That principal quantum number was denoted by small n. Principal quantum number was denoted by small n. What is the work of this principal quantum number? This principal quantum number gives us information about the number of electrons present in an atom or orbit. The number of electrons present in an orbit or orbital also we can find. Okay. So how many number of electrons? So he given one formula for the calculation of maximum number of electrons in an orbit or shell. Both are same. The formula is 2n square. N is nothing but number of shell, means either first shell or second shell or third shell like. Suppose see, I want to know in first orbit or shell how many number of electrons are present. So when first while I am talking about the first orbit, then I will take here see, value of n is 1. 1 means K shell. Value of n is 2 means L shell, 3 M shell, 4 N shell, 5 O shell, like that. We have an n equal to 1, that is the first shell, name of the shell is K shell. If anybody asks what number of electrons present in K shell, then you have to apply this formula, that is 2n square. So K shell, how many number of electrons are present? Let us see. K shell. K shell means n value is how much? 1. N equal to 1. Just substitute that value here. 2 into 1 whole square means 2. So, according to this principal quantum number and this formula 2n square, K shell can accommodate 2 electrons. Means in first orbit there will be 2 electrons. Come to the second shell. Suppose if you take L shell, L means what is the value of n? 2. Value of n is 2. So, if you substitute that value in 2n square formula, then 2 square means 4. 4 2s are 8. So, L shell can accommodate 8 electrons. K shell can accommodate 2 electrons. Comes to the M shell. M means what is the value of n? 3. So, 2 into 3 whole square. 3 through 3, 9 2s are 18. So, M can accommodate 18 electrons. 3 square means not 3 2s are 6, that is 3 into 3. Right? So, 3 square means 3 3s are 9, 9 2s are 18. So, M shell can accommodate 18 electrons. Comes to the N shell, 2 into 4 whole square, 4 4s are 16, 2s are 32 electrons. So, N shell can accommodate 32 electrons. So, from this principal quantum number, we can know how many electrons are present in the given orbit or shell. And one more information also we can know about this is the size of the orbit. Means, see here, higher the value of n, greater the distance from the nucleus. See, suppose it is the nucleus. When n equal to 1 means this is the first orbit which is nearer to the nucleus. If I take the second orbit, it moves some far from the nucleus, not like first orbit. If you keep on moving like that, so n value is increasing, means first orbit, second orbit, third orbit, fourth orbit, like n value is increasing, the distance from the nucleus also increases. Right? So, that is, if the distance from the nucleus is increasing, so the energy separation between the two shells decreases on moving away from the nucleus. So, the energy difference also here we can take. The greater the magnitude of the energy also, the distance from the nucleus is increasing, so the difference, the distance, greater magnitude of energy of the electron in the orbit, energy also differs. Here see, E2 minus E1. Energy difference between these two orbits will be greater than the energy difference between the third shell and the second shell. So, number of shells are increasing, the energy also increases. The energy difference between the two shells, okay, that decreases, but here this is the relation we can see. So, from this principal quantum number, two things we have to learn. The one, it gives the information about the number of electrons present in an orbit and size of the nucleus or size of the atom, either the big or small, like that we can know about by using this information. Right? Now come to the second quantum number. The second quantum number is azimuthal quantum number. So, this azimuthal quantum number was given by Sommerfeld, and this azimuthal quantum number also known as angular quantum number or secondary quantum number. Angular quantum number or secondary quantum number or azimuthal quantum number. Okay, the letter we denote to represent this azimuthal quantum number is small l, represents with small l. And one more thing, always this azimuthal quantum number value will be lesser than principal quantum number. Always n should be less than l, means n should be greater than l, l should be less than n. Okay, if n equal to l, not possible, n is less than l, also not possible. Always n value should be greater than l. Okay, see here, when l equal to 0, then that subshell is called. See here, according to this condition, when n equal to 1, L value should less than n, right? So, L value will be 0. L equal to 0 means that subshell or orbital. What is meant by orbital or subshell? The probability of finding an electron is maximum, is called its orbital. Okay. Here I will give you one information that yes, where electron is present, in the first orbit or in the second orbit electron is present. Okay, in the second orbit where electron is present, see suppose it is the nucleus, it is the first orbit and it is the second orbit. Second orbit electron is present. Where electron is present? Either here, 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 here. Where? Exactly where the electron is present. That information we can get through orbitals. The probability of finding an electron maximum is called its orbital. Such orbitals generally we follow 4, that is s orbital, p orbital, d orbital, f orbital. Orbit is called shell. Orbital, subshell, right? So when n equal to 1, L can have less value, means 0. L equal to 0 means that subshell is S, that is called S orbital. When n equal to 2, L can have 2 values, means L can have either 0 or 1, because L should be less than n. The numbers less than 2 means either it can be 0 or 1. So when n equal to 2, L can have 2 values, those are 0 and 1. So there is a possibility of s orbital and p orbital. When L equal to 0, that is s orbital. When L equal to 1, p orbital. When L equal to 2, d orbital. When L equal to 3, f. When L equal to 4, g subshell, like that. Here when L equal to 0, 1 means 2, S and P it can be. If you take n equal to 3, if you take n equal to 3, L can have 3 values, that will be 0, 1 and 2. Means when n equal to 3, means in third shell or in third orbit, there will be a possibility of finding an electron in 3 orbitals. Those are S, P and D orbitals, right? When n equal to 4, when L equal to 3, then that is F subshell, right? So when L equal to 4, Z subshell, like that. But the condition is always L value should be less than n only. It is not equal or not greater than n. Okay. So this is this azimuthal quantum number gives us information about the electrons, means so this L value, L equal to 0 S subshell, L equal to 1 P subshell, overall from this azimuthal quantum number, what is the information we can get? The shape of the orbital. Azimuthal quantum number gives us the information about the shape of the orbital. How it gives the information about the shape of the orbital, let us see here. When the information here, how many number of electrons are possible, how many number of electrons are present in this information. See here, S subshell, it has 2 electrons, D subshell has 10 electrons, G subshell has 18 electrons, P subshell 6, F subshell has 14 electrons. How come we know this number? S shell has only S orbital has only 2 electrons, P orbital has 6 electrons. How come we know this information? This information will be given by the magnetic quantum number. When we study the magnetic quantum number, we can understand how the electrons are accommodated in particular orbitals, right? Okay, see here, maximum number of electrons present in a subshell, formula will be given is 2 into 2L plus 1. Maximum how many number of electrons can be accommodated in a one subshell, the information will be given by 2 into 2L plus 1. If you want to know in S orbital how many number of electrons are present, for S, what is the value of L? 0. 2 into 0 plus 1 means 1. So 2 into 1, 2 electrons. So S subshell can accommodate 2 electrons. If you want to know how many number of electrons are present in F, right? So what is the L value for F? L value for F subshell is 3. Just substitute that 3 here. Then 2 into 3 plus 1. 2 3s are 6 plus 1, 7 2s are 14. So F subshell can accommodate 14 electrons. How this F subshell can accommodate 14 electrons? The information we can get from the magnetic quantum number. This is the information we can get from azimuthal quantum number, right? Next, come to the magnetic quantum number. See, this magnetic quantum number was proposed by Landé, and the letter we denote this magnetic quantum number is small m. Okay, principal quantum number small n, azimuthal quantum number small l, like that only magnetic quantum number is small m. See, what is the purpose of this magnetic quantum number? N gives the size, about the information about the size, and L will give information about the shape. Like that only here, magnetic quantum number gives the information about the orientations, spatial orientation of the orbital. Let us see what is that spatial orientation like. And see here, the first condition I said, n cannot be 0. If n 0 means there is no orbit. If there is no orbit in an atom, then where electrons will be? So, n will never be 0. N equal to, when n is not equal to 0, n should be n equal to 1, 2, 3, 4 and so on like. What about L value? Always L value should be less than n. L less than n. Okay. So, n minus 1 it should be. L value will be always n minus 1. So, this magnetic quantum number will depends upon the L. N is independent, it will not depend upon any quantum number, but L is depends on n. L depends on n. Then what about M? M depends on L. How it depends on L? See, here in magnetic quantum number we will take the spatial orientation of the electrons present in an orbital. Okay, so the formula we are going to follow is M equal to 2L plus 1. M equal to 2L plus 1. See here, when L equal to 0, here we have, when L equal to 0, M will have 0 value. Means how? When L equal to 0 means M equal to 2 into 0 plus 1. So, 2 into 0, 0 plus 1 means 1. So, this L equal to 0 means what is that? S orbital. S orbital. So, when L equal to 0, that is S orbital. S orbital has only one orientation. Only one orientation. This 0 indicates one value. That means one orientation. Comes to here. When L equal to 1 means p orbital. It is S, it is p. When L equal to 1 means that is p orbital. For p orbital, if you substitute in this formula, 2 into plus 1 equal to 1 means 3. For p orbital, M has 3 values, means it has 3 orientations, means p orbital has 3 orientations. S orbital has only one orientation. P orbital has 3 orientations. Come to the d orbital ones. What is the L value for d orbital? It is 2, right? So, substitute in this formula 2. Then you will get 2 into 2 plus 1 means 5. So, for D means it has 5 orientations. D has 5 orientation. For F, if you take, it will value comes 7, means it has 7 orientations like, right? So, N is independent, L depends on N, M depends on L. Always M value should be lies in between minus L to plus L, including 0. If you are taking L value 1, for this M we said 3 values. That 3 values should be within 1 only, means minus 1, 0, plus 1. If for d orbital L value is 2, so M values will be within that 2, either plus or between plus or minus 2, means plus 2, plus 1, 0, minus 1, minus 2, like that we will have. So, M depends on L, L depends on N, N is independent. Let us see here. What is orbital? Already I explained that what is the orbital. The place where the probability of finding an electron is maximum, that is said to be orbital. Here we are discussing about the 4 orbitals, s orbital, p orbital, d orbital, f orbital. According to the magnetic quantum number, we know that s orbital has only one orientation, that is 0. S orbital has only one orientation, that value is 0. Whereas come to the p orbital, it has 3 orientations. What are those orientations? Px, Py and Pz. What is that? Px, Py, Pz. According to the M magnetic quantum number, D has 5 orientations. What are those 5 orientations? dxy, dyz, dzx, dx square y square, dz square. Right? So, and also for D, M has 5 orientations, right? M has 5 orientations, but in these 5 orientations, the value should be lies between -2 to +2, including 0. That's why we have written here plus or minus 2, plus or minus 1, plus or minus 1, plus or minus 2. Actually, if you allot the numbering, that will be -2, -1, +2, +1, here 0. In some books, if you read, dz square will allot always with 0, and here pz also will always allot with 0. But actually in some books they will give px is -1, py is 0, pz is +1 like. So no need to worry about that values. But the thing is, here p has 3 orientations, those are px, py, pz. D has 5 orientations, dxy, dyz, dzx, dx square, y square and dz square like. That is the thing about the orientations and how many number of orientations we have. These orientations only we are calling as the degenerate orbitals of D or degenerate orbitals of P. S has no degenerate orbitals because as S has only one orientation, that is 0, right? So now come to the important point, these are their orientations. See, according to the magnetic quantum number, S orbital has one orientation, that is C. It can move in all directions, non-directional we can say, or unidirectional we can say, see here. So, but whereas come to the P orbital, P has 3 orientations. What are those orientations? That shape will be, means P orbital shape is, S orbital is spherical in shape, P orbital is in dumbbell, D orbital is in double dumbbell, and F orbital shape is complex shape. That one see, in azimuthal quantum number, where we are talking about this S subshell, P subshell, D subshell, here S subshell value is spherical and P is dumbbell, D is double dumbbell. It gives the information about the shape, right? So here those are these shapes. S orbital, it is spherical. P orbital, it is dumbbell. It has 3 orientations. Those orientations are px, py, pz. Whereas come to the D orbital, it has 5 orientations. One is dxy, dyz, dzx, dx square, y square and dz square. See, this dz square value will be, this is see, means it is on one plane it will be, whereas come to the dx square, y square, it is along the plane, along the x-axis and y-axis. Whereas come to the dxy, dyz, dzx, they are in between the axes. Those double dumbbells are, this is double dumbbell, so each dumbbell will be in between the axis. Whereas come to the dx square, y square, those are along the axis. Okay, this one will be on z. Electrons will be, we can find in dz square, there only in the maximum, right? So this M is giving information about the orientation of the orbitals. Now last one is spin quantum number. What is the information given by this spin quantum number? As we know that, now first of all, what are the previous 3 numbers we have learned? That is the information in which shell electron is present given by N, and in that shell in which orbital electron is present given by L. Again in that in which degenerate orbital electron is present, given by M. Again we know that each orbital can accommodate 2 electrons. Again, about which electron we are talking, the information will be given by the S spin quantum number, generally will represent with S. Okay, so at the starting of this video I said how to address one person. We should know the city, we should know the area, we should know the apartment. Now just you compare where the electron exactly is present. This N gives information about the city, means in which orbit electron is present. This L gives information about in that orbit we have orbitals, S orbital, P orbital, D orbital, F orbital. In which orbital electron is present, that information will be given by L. Again, in that SPDF we have a degenerate orbitals Px, Py, Pz, dxy, dyz, dzx, dx square, y square, dz square. So in which degenerate orbital the electron is present? Let us see. If you take n equal to 1 means only one shell. S orbital, if you take, S can have only one value, means it has only one orientation. That's why I am taking only one box here. Whereas come to the P orbital has 3 orientations. So I should take here 3 boxes for P. According to the magnetic quantum number, D has 5 orientations, means D orbital it has a 5 orientation. So we have to take 5 boxes for D. This is not X, not Y, not Z, because it is unidirectional, right? But comes to the P, one is Px, one is Py, one is Pz. Whereas come to the dxy, dyz, dx square, y square, dzx, dx square, y square, dz square, like information we are getting. So each orbital can accommodate only 2 electrons. So S orbital can accommodate 2 electrons. P orbital can accommodate 1, 2, 3, 4, 5, 6. P orbital can accommodate 6 electrons. D orbital, each orbital can accommodate 2. 2, 2, 2, 2, 2. So it can accommodate 10 electrons. That is what we have studied here. S subshell 2 electrons, P subshell 6 electrons, D subshell 10 electrons, F subshell it has 7, so it can accommodate 14 electrons. That is what the information. So the spin quantum number given by Uhlenbeck and Gaudsmit, and they are giving the direction of the spin, clockwise direction and anti-clockwise direction. Always first electron will be in clockwise direction and second electron will be in anti-clockwise direction. And to not confuse, while we are talking about the first electron in the orbit or second electron in the orbit, to not get confused, so they have given for first electron plus half and they have given second electron for minus half. S has plus half value, then that we are talking about the first electron. S has minus half, then we are talking about the second electron, like. So the complete information where exactly the electron is present, the information given by the quantum numbers, and on these quantum numbers the how to do the application part we will see in the next video. Okay, so in today's video we have covered Heisenberg's uncertainty principle and quantum numbers, right? Hope you understand, and please do watch the video. Thank you so much.